Nvidia just posted its earnings for the fiscal quarter ending July 2026, and Jensen Huang stood in front of analysts and forecast 70% revenue growth by fiscal 2028. Wall Street called it stunning. But inside a small cluster of research labs, engineers already know that Nvidia's current hardware, the H100, the Blackwell series, all of it, is already obsolete. Not in the way that last year's phone feels slow. Obsolete in the way that a horse-drawn cart is obsolete next to a freight train. There is a new class of chip being built right now that processes AI workloads 1,000 times faster than the silicon you are running today. Most people have not heard about it yet. They will. Here is why the timing matters. We are not talking about a laboratory curiosity that might arrive in 15 years. Cerebras systems, Groq, and a wave of photonic computing startups are already shipping or within 12 months of shipping hardware that breaks the fundamental speed limits of conventional silicon. And the geopolitical dimension is urgent. The CIA director just made a quiet trip to Moscow to warn Russia away from NATO aggression. Meanwhile, the United States and China are locked in a race where the winner of AI compute dominance may determine which nation controls the global economy by 2035. The Department of Defense has already committed $14 billion to next-generation AI compute infrastructure in a single budget cycle. If the wrong hardware architecture wins that contract, or if a foreign competitor reaches this milestone first, the consequences ripple into military intelligence, financial markets, pharmaceutical research, and every grid system running on predictive software. This is not abstract. Two things hang in the balance: national security and your economic future. To understand why this chip matters, you need to understand what has been holding AI back. For the last decade, the dominant paradigm has been the GPU, the graphics processing unit. Nvidia turned GPUs into AI engines because they are brilliant at doing thousands of simple calculations simultaneously. Training GPT-4 required somewhere in the range of 25,000 Nvidia, a 100 chips running for roughly 90 to 100 days. That is not a supercomputer. That is a warehouse full of supercomputers, consuming enough electricity to power a small city. The fundamental problem is that GPUs were not designed for AI. They were designed for rendering video game graphics. Repurposing them for neural networks is like running a marathon in ski boots. It works. People have done it. But the boot was never built for the road. The bottleneck is not raw processing power. It is the constant, grinding movement of data between the processor and memory. Every time an AI model needs a new piece of information, it has to fetch it. That fetch takes time. Billions of fetches per second, and each one costs energy and speed. This is called the memory wall, and it is the core limitation that next-generation chips are designed to demolish. The first thing you need to know about the new architecture is what Cerebras has already demonstrated. Their wafer-scale Engine 3, announced in 2024, contains 4 trillion transistors on a single chip the size of a dinner plate. A standard Nvidia H100 GPU contains 80 billion transistors. Cerebras fits 50 times more processing power on one piece of silicon by doing something no one thought was manufacturable at scale. They build the entire wafer as a single chip instead of slicing it into individual units. That eliminates the communication lag between separate chips entirely. But Cerebras is only the beginning. The deeper revolution is photonic computing, using light instead of electricity to move data. Light Matter, a company founded out of MIT, has built interconnects that transmit data between chips at the speed of light. Electricity through copper wire travels at roughly 60 to 70% the speed of light and generates heat doing it. Photons through optical waveguides travel faster and generate almost no heat. The implication is that the cooling infrastructure currently consuming 30 to 40% of a data center's total energy budget begins to disappear. That is not a minor efficiency gain. That is a structural reinvention of what a data center is. Here is the part that should genuinely recalibrate how you think about this. The 1,000 times speed improvement is not coming from one innovation. It is coming from 3 simultaneous breakthroughs converging at the same moment, and that convergence is what makes this moment different from every previous chip announcement. Groq has built what it calls a language processing unit, an LPU, specifically architected for inference, which is the act of running an AI model after it has been trained. On standard benchmarks, a single Groq LPU delivers inference speeds of 500 tokens per second. A comparable Nvidia H100 delivers roughly 60. That is already an 8 times improvement on shipping hardware today. But Groq's roadmap targets 100 times improvement by 2027 through a combination of larger on-chip memory, deterministic execution, meaning the chip never waits, ever, for any reason, and photonic data transmission between nodes. Stack that on top of the wafer-scale integration from Cerebras and the near-zero latency optical interconnects from light matter, and you are compounding multipliers. 8 times, times 20 times, times 8 times. The math gets uncomfortable fast. 1,000 times is not a marketing number. It is a conservative engineering projection based on multiplying gains that are already individually measured and verified. The mechanism underneath all of this comes down to one core problem that these chips solve in 3 different ways. Every traditional chip spends most of its time waiting. The processor is fast. The memory is slower. So the chip sits idle, millions of times per second, waiting for data to arrive. Engineers call this the von Neumann bottleneck, named after John von Neumann, who designed the basic computer architecture in 1945. That architecture has not fundamentally changed. Cerebras eliminates the bottleneck by putting the memory directly on the chip, 40 gigabytes of on-chip SRAM on the WSE3, compared to roughly 80 megabytes on a standard GPU. The data never leaves. Groq eliminates the waiting through deterministic scheduling. The chip's compiler pre-calculates exactly when every piece of data will be needed and preloads it, so the processor never idles. Light matter eliminates the energy cost of moving data between chips by replacing copper with light. Think of it this way. The current system is like a massive library where the books are kept in a separate building across the street. These new chips move the entire library into the same room as the reader, arrange the books in the exact order they will be needed, and replace the courier with a beam of light. The waiting stops. The heat stops. The speed explodes. There are real complications here, and you should know them. First, these chips are extraordinarily difficult to manufacture at yield. Cerebras wafers are so large that a single defect anywhere on the chip can theoretically compromise the entire unit. Cerebras has solved this with redundant cores. If a transistor cluster fails, the chip routes around it. But this adds design complexity that pushes the price per unit into hundreds of thousands of dollars. That means only the largest cloud providers can afford the hardware, concentrating AI capability into fewer hands. Second, the software problem is severe. The entire AI industry has spent a decade writing code optimized for Nvidia's CUDA programming environment. Groq, Cerebras, and Photonic systems all require developers to rewrite their models from scratch or use new compilers that are still maturing. History shows that the best hardware does not always win when the software ecosystem is entrenched. Betamax was technically superior to VHS. The transition cost is real, and it creates a window where the most powerful hardware sits underutilized simply because the tooling is not ready. For you specifically, this matters in ways that are arriving faster than most people expect. If you work in any field that currently purchases cloud compute, software development, biotech, financial modeling, content creation, logistics, your cost per AI query is about to drop by orders of magnitude. What costs $1 today may cost a fraction of a cent by 2028. That sounds like good news, and it partly is. But it also means that tasks currently considered too expensive to automate become cheap. Legal document review, radiology screening, drug interaction analysis, customer service at genuine human quality. The economic justification for human labor in those roles changes when compute becomes nearly free.